regarding binary heaps. And that material that is on Blackboard, if you go to Blackboard, you'll see that there are two folders that we are going to be tackling. One of them contains trees in binary heaps and priority queues. That's what we are going to complete today. And there'll be one more topic. And that one more topic is about sorting and sorting techniques. And we are going to talk about that next week. And we're going to conclude the class. So that's the how the future of these things translates to. So now I'm going to share with you a white page, and then we are going to begin our discussions regarding binary heaps. Now, before I talk about binary heaps, let me go back and talk about priority queues. We saw priority queues and the discussion of the priority queues last week on Thursday. And we talked about it in brief, and the demonstration of it was a queue where the dequeuing strategy, the dequeuing or the serving strategy is based on the priority key. So you have a priority key. Imagine that you went to an RMV or in a queuing system, but you get a code or a ticket that tells you when you're going to be seen. So it doesn't matter when you arrived, because your key determines where you're going to be served, nevertheless. So even if you arrive at the second person or the third person, you might be able to be seen before the first person. That would be like a priority. So you're seen with priorities. Now, in our discussion last time, we talked about how do we implement this, how to implement this. That's what we talked about last time. And we said, well, from a normal, not really layman's views, you could use many ways of coming up with the priority queues. Remember, in a normal queues that we had before, the first in, first out type of queues, we were able to implement them using an array or a vector, and we were able to implement them using a linked list. So we started thinking about what is the complexity, the time complexity involved in using the array or a linked list to actually implement these things. So we came up with a couple of things. Supposing we used an unsorted array. Now, an unsorted array is just an array of items with no particular ordering, whether ascending or descending, no particular ordering of them. Now, if we were keeping items in an unsorted array, what would be the complexity of adding an item, adding one item? And what would be the complexity of removing an item, remove item here? Now, if you have an unsorted array, it means that supposing you had an array, I'm going to just draw it here, an array looking like this. This index 0, index 1, index 2, index 3, index 4, 5, 6, 7. So this array can hold 8 items rather. And if these items came 4, 7, 3, 2, 1, the question with unsorted array is, how would you put them into the array? Well, with an unsorted array, it doesn't matter. 4 arrives first, we're sticking 4 here. 7 arrives, we just take it into the next cell, which is empty. So 7 goes here, same for 3, same for 2, and same for 1. If 9 arrives, we don't care, we just press 9, whatever it is, or the next empty cell in there. So with unsorted array, we do not need to do any comparison checks, any swaps, anything. Whenever something arrives, we just put it into an array. And therefore, the time complexity of inserting an item into the unsorted array became O of 1. Okay? Now, what happens when we want to remove these items? Let's take a simple example of where the priority is based on how high the number is, or the larger the number is high priority. So in this case, I think we all agree that 9, this number over here, 9 would have a higher priority than all of them. But how would we have known about 9? We would have come there and basically start searching for the largest item in the array. So we would perform a search, right? And we know how to perform a search. We basically do just compare. We assume the first number here, 4 is the largest one. We compare with 7, 7 becomes the largest one. And we go on, we go on, we go on until we find that 9 is the largest number. So in the worst case, or in most cases actually, would have had to do unequal comparisons to the number of items in the array to determine where the item is. Okay, so let's suppose that that number is 9, which here, so and this array had 7 items, so we'd have had to check, a couple of comparisons until we find it. So we'd have had to do n comparisons. Removing the item is not hard. Possibly we just have to swap with the last one and then disconnect it. So this will be O of n to remove the item. Okay, if it's not understood, please you can write that on the text so that I can be able to address it if you don't get why this will be O of n. We talked about last week. If you don't have, if you'd like me to check it out, let me know. Similarly, if we had unsorted linked list, it will be a similar thing, right? So remember, for this linked list, things will look like this, right? So supposing this was 4, 7, 3. So maybe not like that. So when these items come, so let's build it properly. So when these items come, it doesn't matter where we put them. So 4 comes, we stick in 4 here, okay? And then 4 becomes there. Then 7 comes, we create a node for 7. And then we just connect 7 to 4. So now 4 is the last one. 3 comes, we do the same. And when we discussed linked lists, we said that this is called insert head. So we are inserting at the head. So we'll create a function called insert head, and we're inserting these nodes at the beginning of the linked list. All right. What I mean by that is that the pointer to the head is always pointing to the newest added item. Now, because we're not really checking where the tail is to add items, we're just inserting at the head. So inserting with unsorted array, linked list becomes O of 1. But what about removing the item? We'd have to find out which is the largest item in the linked list. So we'd start at the head, compare all of them until we find the first one, the largest one. And therefore, just similar to the array, it will be O of n. I'm hoping that we can all see that. What about if we decided to have these things as sorted? So what about a sorted array? Now, let's see how a sorted array would work. So I'm going to remove these guys here. Okay, these guys are gone. So let's do now a sorted array. With a sorted array, when 4 comes, 4 would have been the only items in the array. 4 would have been the only items in the array. So we stick in 4 here, there is no problem. So let's imagine that the highest priority is the items with the largest number. So when 7 comes, there are a couple of things we can do. We can compare 7 and 4, push 4 or shift 4 to the right-hand side and stick 7 here. But that would be too technical to do. So the easiest way to do is get 7, stick it to the empty box, and then perform comparisons going to the left-hand side, which means we get 7 here. We compare 7 and 4. 7 is greater than 4, and therefore we swap 7 and 4. So in our new array, 7 will be here. We swap it with 4. 3 comes, we stick 3 here. We compare 3 and 4. 3 is smaller than 4, so we don't do anything. 2 comes, we compare 2 and 3. 2 is smaller than 3, so we don't do anything. 1 comes, 1 is smaller than 2, so we don't do anything. 9 comes, we insert it at the back, and then we now start with a comparison. 9 is greater than 1, so we swap them. So if we were to redraw the array now, 9 will be here, sorry, 1 will be here. 9 compared with 2, 2 is smaller. 9 compared with 3, 3 is smaller. 9 compared with 4, 4 is smaller. 9 compared with 7, 7 is smaller. And then there's now space where we can put 9. So you'd agree with me that to insert an item into an already sorted array would have to do as many comparisons, at the worst case, as many comparisons as the number of items in the array. For instance, in here, there are 5 items in the array. When we started 9, we did 5 comparisons to determine the actual proper location for 9. So inserting an item in a sorted array becomes O of n. What about removing an item? Well, removing an item is easy because that item, the item in here, is always the largest item, correct? It's always the largest item. So the item here is always the largest item, and therefore we know, where the largest item is. So removing becomes O of 1. Similarly to sorted linked list, we're doing the same thing, right? With the sorted linked list. So when we insert, first of all, we go through the entire list to find out where to insert an item. Therefore, the comparisons could be O of n. But removing the item is just disconnecting the one that would be the front one, where the largest one is. So that would also be O of 1. So that's what we saw last time regarding how we could have this priority queue, right? How we could get to the problem of the priority queue. We are dequeuing an item based on priorities. So how do we add items? We create this idea or these priority queues using either unsorted array or unsorted linked list. This is how our time complexities will be affected. So we've said then, when we discuss this, that it's almost like we are in two extremes. Yeah, we either choose to add with O of 1 and remove with O of n, or we add with O of n and removing with O of 1. And you say that, well, it's inefficient in one way and better on one side. So we started asking ourselves, is there a better technique to be able to bear to this problem? Now, one thing we have seen is that if we had binary trees, I'm not using here, so I'm just putting here just now, just something here to just tell you we're going to check this. If we had binary trees, we saw from dealing with binary trees and binary search trees and AVLs, we saw that we could add items with O log of n, and we could remove items with O log of n. That's what we saw when we did BSTs then. So the question is, can we take advantage of the binary trees to be able to perform toward an item with O log of n and remove at O log of n? And the answer to that question is yes, we can do that. But now we change this, instead of binary trees, we call this binary heaps. So binary heaps is an abstract data type that we can use to implement a priority queue where we are able to add items with O log of n and removing items at O log of n. All right, so let's go to that. So binary heaps, okay, and this is an ADT, editing, where we can make these guys out. But this that we can use to implement to efficiently, maybe what I'm looking for is efficient, to efficiently implement a priority queue. Okay, so we're trying to get a priority queue, but we're trying to see how best can we implement this. And we're seeing the best data structure for that could be the binary heaps. So that's what we're going to be discussing, what the binary heaps are. So a couple of things about them. So there are two important things with binary heaps. Number one is the structural properties. You can write this down, by the way. So structural property, we say we want, so edit that can to efficiently implement a priority queue as an array. So I'll say here as an array. Okay, so we are going to represent this as an array, mimicking a binary tree. Because we know binary trees can be done with O log of n. So we are doing this. So we are implementing an array that mimic a binary tree. Now, how do we do that? So last time when we discussed different types of trees, some classification trees based on structure, we came up with two kind of trees. We came up with full binary trees, and we came up with almost complete or complete binary trees. So for the binary heaps, the structure property means that this tree must be complete or almost complete. I think from last time you saw that if we had a tree which is complete or almost complete, we can efficiently put it into an array. This is what I mean. A complete tree looks like this. Let me just put some numbers. That's a complete tree. Don't worry about the ordering of them. Something like that's a complete tree. That's a complete tree, etc., etc. Why am I saying these trees are complete or almost complete? For a complete, almost complete tree, all levels are filled up, with sometimes the exception of the last level, which if it's not filled up, all the nodes are pushed up to the left-hand side. So all levels are filled up, with exception of the last one, where if it's not filled up, all the nodes start from the left-hand side. So ideally, we have top to bottom, left to right, top to bottom, left to right. So that's what we have, top to bottom, left to right, and that's the order, right? So we can read these things from level 0, level 1, level 2, etc. And each level must be filled up. And if the last level is not filled up, the nodes must come from the left-hand side. And if we're representing this in an array, then the root would be at index 0. Then the one on the left should be index 1, index 2, then index 3, index 4, and so on. For example, in this case, would have been here. This would have been index 0, index 1, index 2, index 3, index 4, etc. So far, so good. So these can be represented an array as 7, 3, 2, 3, 2, etc. 7, 3, 2, 3, 2, as read from top to bottom, left to right. Like that. And we also saw, so index 0, index 1, index 2, index 3, index 4. If we are programming it, if we wanted to know the parent of this guy here, we just need to go to the index. So parent index is equals to the current index minus 1 divided by 2. So if you want to know the parent of 2, the index of 2 is 4. So 4 minus 1 is 3. 3 divided by 2, we're doing integer division. 3 divided by 2 is 1. And therefore, the parent of 2 must be this guy here, which is 3. So that's how we know. So the parent of 2 is 3, which is this guy over here. Does it make sense? So far, so good? So that's what we call a structural property. I would like for you guys to communicate back so that I can know that you understand. So that's a structural property. The next thing is something called ordering property, which is exactly similar to, similar in nature. Ordering property. How do we keep these items? Do we have a certain order about how the items are kept in the array? Ordering property, or in the tree, ordering property. Now, we have to think about the heaps in two different ways. Now, you could have a heap where we have maximum, the larger the number, the higher the priority, or we could have the lower the number or the smaller the number, the higher the property. So we have max heap, and we have min heap. All right. So what is the ordering property? For max heap, if you had a node X, then the priority of X must be greater or equal to priority of the children. Priority of left and right child. Okay. So similarly, for the min heap, if you had a node X, then priority of X must be less or equal to priority of children. So it's not too complicated, right? It's not too complicated. The idea is to understand that we can implement this as a max heap, where the larger, so if you think about this, the largest item will be the root. And if you think about the min heap, the smallest item will be the root, right? So we arrange in that order. So these are the two main ones. These are the only properties that we need to talk about. Structural property, in order for this to fit it as an array, then it must be complete, almost complete. Otherwise, you'll not be able to store it in an array. So complete, almost complete. And the next one is ordering property. We have max heap or min heap. Max heap means you have node X, and the priority of X is greater or equal to the priority of left and right child. And for the min heap, for node X, the priority of X is less or equal to the priority of children. Okay, any questions for me? All right, let me show you a couple of examples. So for example, for max heap, this could be a max heap. Say we have 7, 2, 1. That's max heap. If you look at this, 7 is greater than both its children 2 and 1. Another example, 7, 2, minus 1, 0, I don't know, 3. Again, that's a max heap. If you look at it, all the levels are filled up apart from the last level. And at the last level, all items are coming from the left-hand side. And if you look at all the parents, the children are smaller than the parents. That's a max heap. Examples of min heap. Okay. That's a min heap. Why? 0 is smaller than both 1 and 2. Okay. So this 0, again, the 1 and 2 are smaller than 0, and 1 is smaller than minus 1 and 10. You see that? So these are mini heap. So the first question should come to your mind is, how do we build this? How do we build this given some data? Is that the question coming to your mind? How do you given this, given some data? How do we build this given this? By the way, is this a mini heap? You tell me if I give you this number. Is that a mini heap? Someone, is that mini heap? Is that a mini heap? I'm not particularly certain. Do we have people here in this class today? Okay, say it says no. Why is it not a mini heap? Okay, 10. Small is not the root. Small is not the root. Small is 3. Okay, another question. Is this a heap to start with? Is this a heap to start with? If you look at this tree is not a complete or almost complete tree. Why? Level 1 is filled up, level 2 is filled up, level 0 is filled up, level 1 is filled up, level 2 is not filled up, but the items are actually on the right hand side. So you can't actually make an array out of this. So this is wrong, right? This is wrong. This is not a complete tree. You cannot make an array out of this at all. So this will be, rejected whether or not the items queried properly. So that's an important. So let's go back to the other central question. How do we build these given some data? So implementing binary heaps. For the, yeah, I can hear you. Hello, did somebody speak? Did somebody speak? All right, nobody spoke then. So implementing a binary heap. So how do we go about implementing a binary heap? So for the sake of argument and to make it easy, I'm going to just look at the idea of max heap. Remember, coming from those definitions that we had, that should be as simple as well, right? Given where we are coming from. The min heap is just the reverse of the max heap, given this, right? So the min heap, priority of x less or equal to priority of children. And here, priority of x greater or equal like that. So this is just the same, only that we're reversing this. So why don't you give me some numbers on the chat? Give me some numbers. Okay, so we got 5, we got 7, be quick. We got 13, we got 37. Keep going. We got 10. Keep going. We got 18. We got 25. Keep going. Make 6. All right, let's, and then we have 21. So we're going to stop there. So these are the numbers that are come. So how do we implement a binary heap? 2 techniques. We're going to look at them. Number 1, insert items one by one in an empty heap. How does that work? So if you are to insert items one by one in an empty binary heap, we're assuming it's already a binary heap. Let me call it max binary heap so that you know that we are going to do a max one. Then you have to insert one by one, ensuring and maintaining that the heap is made. So 5 comes in first. 5 is the root. And because there's no other items in, then 5 maintains the idea of a heap. 7 comes. Which side should we put 5? 7. Because we are going top to bottom, left to right. That's how that's the only way we can be able to come up with a complete tree. Then 7 should be on the left of 5. Remember, we want to make a max binary heap. So the first thing we do, we compare 7 and 5. Is 7 greater than 5? Yes, it is. And therefore, we swipe them. So now we have 7 and we have 5. And the priority is maintained. 13 comes, we insert 13 here. Then we compare 13 and 7. 13 is greater than 7. So we swipe them. We have 13, we have 5, and we have 7. 37 comes, we stick 37 here. Remember, we have to do top to bottom, left to right. And then we compare that 7 and 5. That 7 is greater, so we swap them. And then we compare that 7 and 13. That 7 is greater, so we swap them. And now we have our tree is a max heap. 10 comes, we stick 10 here. We compare 10 and 13. 10 is smaller, so we don't need to do anything. 18 comes, we put 18 here. 18 is greater than 7, so we swipe them. So we have 37. We have 13. We got 18. We have 5. We have 10. And we have 7. 25 comes, we stick it in here. 25 is greater than 18, so we swipe them. We have 37. We have 13. We have 18. We have 5. We have 10. We have 7. Sorry, this will be 25, and because they swiped. This 25, and then got 18. And then 21 comes. I don't know. 25 is already done. So we have 6. 6 comes here. We compare 6 and 5. 6 is small, 6 is larger, so we swipe them. Allow me to just, instead of redrawing, to just put them in. So 6 and 5. And then 21 comes. We put 21 in here. 21 will swap with 6. 21 will swap with 13. So we'll have 37. We'll have 21. We'll have 25. We'll have 7. We'll have 18. And we'll have 13 here. We'll have 10. And here we'll have 5. And we'll have 6. And the corresponding array now will be 37, 21, 25, 13, 10, 7, 18, 5, and 6. And if you look at our tree, that 7 is greater than 21, 25, 21 is greater than 13 and 10, 13 is greater than 5 and 6, 25 is greater than 7 and 18. So we have been able to make a max heap using this technique, adding items one by one and ensuring that we are able to maintain the max heap property. Now, who can tell me, inserting one items, if the work performed is basically comparisons and swaps, at the worst case, how many comparisons do we have to make for one when we insert one items? So for example, when we entered 21, remember when we entered 21, we compared with 6 and then we compared with 13. Supposing actually we didn't have 21, we had maybe, supposing it was 50, supposing it's 50. or rather, let's have 21 because we already have it. Supposing 50 came in, how many comparisons? Because 50 will have to go to the top. So how many comparisons will have to be made? So remember, when 50 comes, we're going to put it, when 50 comes, let me write it with a blue pen. When 50 comes, it's going to be here. So how many comparisons will have to be made? We'll compare with 10, we'll compare with 21, and then we'll compare with 37. And then we'll shift them all down. So this will be 50, this will be 37, this will be 21, and this will be 10. So if you look at it, we basically have to do 3 comparisons or and 3 swaps to be able to put an item from the leaf all the way to the root. Basically, this is equivalent to the length or the height of the tree. And from our previous discussion, we saw that the height of the binary tree is comparable to O log of n, particularly the tree is complete. Therefore, to add just one item, basically, to add it and ensure that it's in the correct position, that takes us log of n to do. So if you have n items that you're adding to the tree, then you're going to do this work with O log of n multiplied by n, which is big O n log of n. So to add items or to create a binary heap using this technique where we are inserting items one by one and then ensuring that the heap properties are met, that can be done with only n log of n to be achieved. So the question is there a better way? So I'm going to spend the next 5 minutes saying whether there's another better way. So these numbers here, let me write them down because you guys gave them to me. 5, 7, 13, 37, 10, 18, 25, 6, 21. So we have those numbers again. Let me write them down. 5, 7, 13, 37, 10, 18, 25, 6, and 21. So another technique 2, is to assume that items, all these will have items, are already in a heap. And then check for violations and fix. So what does that mean? We'd assume that all these numbers are already in a heap, and then we try to fix them. So how does that mean? We just draw the heap 5, 7, 13, 37. Remember, I stopped to down, to bottom, left, right. 37, 10, 18, 25, 6, and 21. So the first thing is to ensure or to assume that you already have a heap, that this number is in a heap. And then basically you check whether the heap is maintained or the properties are maintained. So if you look at these, that 7 here is a parent, so this one is maintained. 13 here is not maintained. 7 here is not maintained. Yeah, because we already know, So for example, max heap. Example for the max heap here. Remember what we said? Parent must be greater or equal to children, right? To children, left and right. So parent must be greater or equal to left children. So if you compare all of the parents, you see that this is not properly fixed. So how do you go about it? Okay. Start with the last parent, determine the last parent and start from it. Start from last parent, and fix down. Start from first parent and fix down. This process is also called heapification. Heapify. Start from the last parent and heapify. Do we know the last parent? Yes. If you had just had the array, if they were in an array, you'd know the last parent, and you'd know the last parent by doing this, what we have here. Parent index equals to current index minus 1. That would have told us what the parent is. But visually, we can be able to look at that visually. So the last parent visually is 37. So this index 0, index 1, index 2, index 3. So the last parent is 37. So you start from the last parent and fix down. So we check here, 6, I'm just going to redraw one by one, and then we finish. So we'll go to the children, 6 and 21, we compare them. 21 is greater, and therefore we compare 21 now with the parent. 21 and 37, 37 is greater. So this one is okay, we don't need to fix it. We go to the other parent, it's 13. We compare 13, we go to his children. Left child is 18, right child is 25. 25 is bigger than 18, therefore we check 25 and 13. 25 is greater than 13, so we swap these two. Okay, so I'm going to take here just to show that I changed that. So 25 will be here, and here we have 13. Now our parent at 2 is okay, right? Our parent 2 is okay. Remember, in an exam situation or in a kind of situation, you'll need to show all the steps, all the steps. I'm not showing these steps here, but you need to, to have drawn how it will look like and all that. Now that parent is met. We go back to 7 here, and we check 7. We find that 7 and 10, that 7 is greater than 7, so we swap these two. Okay, now when we swipe this, we get this guy, we get this guy out, and now we have 37, and we have 7 here. And because we push this down, we must also check now whether it has disturbed this order. So we check 6 and 21, 21 is bigger, 21 is 7, 7 is smaller. So in this case, we get this guy, we get them out, and now we have 21 and 7 here. Good. Now we go now to parent 0, because now we already fixed this. 25 and 37, that 7 is bigger, so that 7 swaps with 5. So we go up here, we swap this guy and this guy. So this is 37 now, and this is 5. We come up here, we compare 10 and 21. 21 is greater, so we swap 21 and 5. So that goes in. And this will be 21, and this is 5. We compare now 6 and 7. 7 is greater, so we swap with 5. Yeah. And this now will be 7, and this will be 5. And we are done. So if we write this down, it will be that 7, 21, the array now, 25, 7, 10, 18, 13, 6, and 5. So we have again come up with a solution for this by first of all assuming that items are already in a heap and then performing what is called fix down or a heapification process. This still guarantees for us that for the max heap, the item is at the top, and for the min heap, that the lowest item is on the top. Now, if you were to think about this, so the last one we saw that to build it was n log of n. What about this one? Is this one a better technique? Turns out to be better, because by putting all these items here, in worst case scenario, if all items were in this order and we needed to swap them, we'll just have to do n swapping of all these items. And therefore, to build with this one is O, big O of n. So to build a binary heap by first assuming that the array is already a heap and then doing a heapification, at the worst case, we build it at O of n. Okay, so those are the two techniques The exam will include questions asking you to do this and asking you to do this, and other questions on things like this. So it's upon you to take some attention, come back to this video, look at it, understand how this process is done, go to the notes on Blackboard, look at them, and understand how this process is also carried out from there. I'm going to stop there. I'm going to stop there, by performing that share. There is a beautiful website. It's called Visual Algo. Visual Algo, let me check that. If you go to these, visualizing data structures and algorithms, you can play around with this. So if you type the word like heaps or something, let's see, binary heaps, I don't know. Yeah, binary search tree, binary heap, for example. You can play around with it. It will tell you, it gives you some notes, and then it will ask you to create with n log of n, which is adding one items by one. So supposing you have this item one by one, if you go, it will show you, you add them and you keep going. And you could do all again. You can insert one by one, extract max, and do a heap sort, things that we are going to do next week. All right, so that place is called Visual Algo or algorithm. So that should be able to help you to visualize how these things work. All right, everybody, I'm going to stop there now. I'm going to stop there.